Alright, welcome back. This is 6.5, problem number 8, probably one of the more challenging problems in the homework. And what it is we've got this side view of a truncated cone. So truncated means that it would have been a cone, but we cut it short of being a cone. And so what that implies is that this shape is actually revolved around into a revolutions of solid shape that looks something like this. What else they tell us is that there's a 1-inch straw, there's a straw that sticks 1 inch above the brim, and that this whole thing is filled up with fluid that has a certain volume force density, right? Because ounces is a force per inches cubed, that's per volume, so rho is equal to 0.4 ounces per inch cubed, which means that for every inch cubed inside of this truncated cone reservoir, each inch cubed carries 0.4 ounces of force with it. So this is what it is going to look like. Let me make some room. So the first thing I like to start with is to always just draw my shape revolved. So as you can see, I'm taking this long, infinitesimally thin strip, and I'm going to rotate it 360 degrees to sweep it out into this disc. And you'll notice that because I'm integrating with my infinitesimal in the y direction, that the height of this disc is going to indeed be dy, or an infinitesimal length of y. And then the other thing we need to figure out to find the volume of this thing is we need to figure out what the radius is. And why am I looking for the volume? Well, I'm looking for the volume because the force density depends on the volume. So the volume is going to be a crucial step in the right direction. So what is R for every single one of these slices that you could possibly make? Because remember, we're going to be integrating all of these discs from bottom to top of the cup. And so it's important to realize that the radius is the distance from the origin to this curve that they give us, which is a linear. It's a linear equation. And you'll notice that the distance from the origin to wherever that linear equation is at, wherever that line is always going to be x, according to the graph. So in other words, radius equals x. For every single possible disk, the radius is going to equal x from our upper boundary condition to our lower boundary condition. And so the next step is we want to figure out what our small chunk of volume is. dV is representing the infinitesimal chunk of volume of this singular disk. And volume is equal to, for this disk, is equal to the surface area multiplied by the depth. So that's pi r squared multiplied by the depth of the disk, which is dy. So we found the surface area, and then we extruded that using volume multiplying by the height dy. Now the question is if we look at our work formula, work equals F dr, where r is the direction of motion and F is the force. Well, here I have dV, but I'm really interested in what my small infinitesimal chunk of force is for every single one of these disks. And you'll notice up here that we have volume, right? So this is in inches cubed. This is our volume in inches cubed. Well, here is our volume force density. It's 0.4 ounces per inch cubed. So if we multiply that, the 0.4 ounces per inch cubed, and we multiply that by our volume, which is in inches cubed, the inches cubed cancels out and we're left with ounces, and that's our force. That's what we're looking for. So we've just proven there that our small infinitesimal chunk of force is equal to our volume force density times our infinitesimal volume. Alright, so that solves part of the problem. Now the next part of the problem is, what is R? So in other words, we know that we're trying to get these strata of water up to this straw, which happens to be an inch above the top of the cup. And so what we're interested in is for any given disk of water or liquid, whatever it is, we're interested in how far does it have to travel, right? How far is this disk going to have to travel? Because of course work depends on the force and how far that force has to be taken. And so you'll notice here that on the graph that they go ahead and tell you that this is 7 minus y. But let's go ahead and explain why. So the reason why is because, so as you can see here, the straw is 1 inch above the top of the cup. The cup goes from 0 inches to 6 inches tall. And so if we're interested in, for example, how far that this disc is going to have to travel to get to the straw, if the disc is at, for example, 0, it has a full 7 to go. If the disc is perhaps at 2 on the y-axis, then it only has 7 minus 2 inches to go, or 5 inches to go. And of course, once the disc gets up to the very top of the cup, it only has 1 inch to travel because the straw is only 1 inch tall. And so you'll see here that work equals force, which we decided was dF, small chunk of force, and then we've got to multiply that by how far did it go, which is 7 minus y. And so now we're going to fill in what dF equals. Well, dF equals rho dV, and we can expand that out. So this equals rho times what we solved for dV, which is pi r squared, which is actually x squared dy. And so we figured out that r was equal to x for every point. Well, the thing is because we're integrating with respect to y, we're going to need to solve for x in terms of y. Luckily, the problem's already done that for us with this linear equation, x equals y plus 10.5 divided by 7.5. So therefore, dF equals, I'm going to replace rho with 0.4 pi times x, which in terms of y is y plus 10.5, divides 7.5, and that quantity squared, right, x squared, and then all of that multiplied by the infinitesimal depth of dy. Alright, so now that we have all this solved for, we can plug it into the force, or to the work equation, and then we can finally set up our integral and solve for it. So work equals the integral of dF, which we solved to be this thing, 0.4 pi times y plus 10.5 over 7.5 squared. And then, now remember we still have to do 7 minus y, the amount of distance that each individual, what do they call them, discs will have to travel, discs of water will have to travel. And then, of course, we still have the dy, which is part of the dF, to plug in here. Alright, and what are our bounds? Well, we are dealing with discs of water that start at the bottom and go all the way to the top. So in other words, we're not integrating to the top of the straw, because we're only curious about the work it takes to get these discs of water out the top of the straw. But the discs of water only exist from 0 down here all the way up to the top of the cup, which is y equals 6. So we're going from y equals 0 at the bottom of the cup to y equals 6 at the top of the cup. So we'll go ahead and fill this in over here. And now I'm going to plug this into Symbolab. And yes, so we have 0.4 pi times y plus 10.5 divided 7.5 squared times 7 minus y dy. And when we plug that in, it solves the integral and says it's roughly, work is approximately 88.5, And work in the English system is either in foot pounds or inch pounds. Since our volume was in inches, this is going to be inch pounds. So IN/lbs. And that is the approximate work for pumping all of this fluid out of the cup through the straw. So I hope this video was helpful as far as helping you set up the problem. These can be pretty tricky, so I know it took me a while to get a hang of them, and sometimes I still get stumped. So anyways, I hope this helped, and I'll see you next video.